Welcome back to Meaning from Data, Statistics Made Clear. In this lecture, we're going to continue our 4-lecture series that concerns the principles and the concepts involved in trying to organize, describe, and summarize a collection of data when we know all of the data in a population. As you recall, in Lecture 4, we emphasized two things. One was the measures of center, which were the median and the mean. And we also talked about measures of how spread out the data were. In particular, we introduced the concepts of the variance and the standard deviation. So in this lecture, we are going to aim for discussion of the shapes of the data. How do we go about describing the shape of the data? So remember that the big picture of how to describe a distribution was to describe three things: the shape, the center, and the spread. Well, so we'll start as usual with our discussion by looking at histograms. And when we take a histogram of a set of data, we get a shape, because where the size of the different bars will describe the shape of the data. So our strategy in this lecture will be first to identify sort of general characteristics of shapes, and then we're going to later discuss specific kinds of shapes that actually have mathematical descriptions. So the general characteristics of shapes are things like being symmetric, for example. But then the specific ones will come later, which have particular mathematical formulas. So let's begin by looking at an example. Here is an example of a specific set of data. These are, again, the heights of American males. And you can see that this is an example of a set of data that is symmetrical about the center. So it's an illustration of a concept of symmetry. And it could be described by drawing a smooth curve that approximates it, which is a curve like this. Now, here's another example. We're just going to go through some quick examples. This is a histogram of house prices. The histogram of house prices have a different kind of characteristic shape. In this case, it's a shape where there are more data values over here to the right. And the extra values to the right that prevent it from being symmetrical make the shape of this data skewed to the right. So one of the terms that we use to describe shapes is being skewed to the right. And by the way, I always used to forget whether the skewed to the right meant that the big part of the tall part was to the right or the tall part was to the left. And it means actually that the thin part, the long part, is in the direction of that you say. Like skewed to the right means the extra long thin parts are to the right. And we can once again draw a general smooth curve that gives a sense of a skewed kind of distribution. So these are just terms that are associated with general shape characteristics. Here's another collection of bimodal distribution. It has two peaks, and these bi, of course, meaning two. And these were the SAT scores, remember, from the school that gave the test both to 7th graders and to 11th graders. And that's why we have these two different peaks. Well, these are generic characteristics of shapes, and they're handy summaries, and they help to give a sense of the shape. But sometimes a shape has a specific mathematical formula description, which then gives a lot of valuable information. But let me first, before we go on to talk about these shapes that have a mathematical description, let me give a little bit of rather pessimistic view of our enterprise. And that is that any possible shape is a possible shape of a distribution. In other words, if you look out at the horizon and you're in Colorado and you look out at the horizon and you see these mountain peaks and you say, isn't that a beautiful sunset? Well, that could be a description of a histogram of a collection of data, right? You just put little bars at exactly those heights and that could be it. or the New York skyline. The same thing. That could be a histogram of data. So we have to be realistic about our hopes here. We're trying to describe every possible shape, and what we're going to do in order to be somewhat successful is to realize that in real situations, collections of data often have shapes that have certain common characteristics. And that's the kind of thing that we're going to be trying to capture. So let's start right now with the simplest shape that a distribution can possibly have. And that is a flat line. That's the simplest. So let's start with something really simple. Flat line. And these distributions are called uniform distributions because it's a completely flat line. So for example, let's suppose that we take a die, like this die, and we roll it 1,000 times. And we take a record of how many times it came up 1, how many times 2, 3, 4, 5, and 6. Well, we have an expectation about how the values of those throwing of the dice would come out. Namely, we would expect to get about the same number of 1s, 2s, 3s, 4s, 5s, and 6. And in fact, we did this. And here are examples of 4 times when we threw 1,000 dice each time and recorded how many 1s, 2s, 3s, 4s, 5s, and 6 occurred in each of those 4 experiments. Now, first of all, I have to confess, we didn't really throw the dice. We used a computer to simulate the randomness, which is useful and easier. But I just wanted to make a few observations about these results. First of all, as expected, in all cases of throwing 1,000 dice, in all of these cases, we expect that we have about the same number of each of the 6 numbers. Now, it's possible, by the way, just by random luck, that all of them would come out to be a 3. You know, that's possible. Extremely unlikely. But we expect them to be about the same number for each one, and that's correct. Now, these things are approximated by this distribution. I mean, in our minds, we say, really, we should have them exactly the same. That's sort of the correct approximation of the concept of the world that is occurring when we throw dice that are equally likely to come on each side. And there's a mathematical formula associated with this distribution. It's a very simple formula. The formula is that for every value, the answer is the same. C is a constant. You get the same value. But let me point out something about this value in the case of dice. We take one die and we throw it 1,000 times. Then what is the expectation for how many times each individual number should arise? Well, it's 1/6 of 1,000. If you divide 6 into 1,000, you get 166 2/3. You don't get a whole number. You get 166 2/3. Well, what does that mean? That means that the expected value, the uniform distribution that is approximating the actual answers, cannot actually be the answer for any experiment, because the dice never come up 166 2/3 time. That's not going to happen. It's a whole number. So the point is that the approximation of this experiment is a function whose value is not ever going to be precise. And in fact, there's a great quotation about models. What we're describing here are models of a distribution. George Box said the following quote, "All models are wrong. Some models are useful." And this uniform distribution illustrates that. We cannot expect that the model is exactly right, but it's useful because it captures a concept of what the shape of the data really are likely to be. And what we're going to be talking about later in this lecture, and in fact, as an important principle of statistics in general, is that if you make certain kinds of assumptions about the processes that are generating a collection of data, we are led to expect certain kinds of shapes. And one thing that we're going to explore now is certain kinds of generating processes that lead to different kinds of shapes. And before we go on to that, though, let me just make one quick observation. The uniform distribution is not the uniform distribution. It's actually a whole family of distributions, namely one for every constant value. In the case of dice and throwing them 1,000 times, the constant value was 166 2/3. Whereas if we were doing something else, even as simple as throwing the dice a different number of times, like 6,000 times, then the uniform approximation would be 1,000 occurrences of each of the numbers. So it's actually a family of distributions, and that's going to be also characteristic of the different shapes that we'll discuss now. So let's take now a different kind of a situation and see what kind of shape distribution we'll expect to be generated from that physical occurrence. We talked before about this occurrence, this experiment that we could do of going to a toll booth in the middle of a road and measuring, say, for every Wednesday between 3 o'clock and 4:40, that's 100 minutes, we sat down at the toll booth and we measured for every minute how many cars arrived during each of those 100 minutes. And then we did that for 10 Wednesdays in a row to get 1,000 occurrences of cars arriving for each minute. So then we could make a graph that captured that data, where we said, well, how many times, for how many minute intervals did no car arrive? And for how many minute intervals did one car arrive? For how many minute intervals did 2 cars arrive? 3 cars, 4 cars, 5 cars, 6 cars? Well, that gives us a collection of graphs. And here, once again, and as before, this is actually a collection of 4 computer simulations of this occurrence. And the computer simulation is assuming that on average 6 cars arrive per minute. That is, we just took all of the total number of cars that arrived during that 1,000 minutes, and there were 6,000 cars. So the average number of cars per minute was 6 cars per minute. But some minutes, none arrived, some 1 arrived, and 2, 3, 4, 5, and sometimes many arrived. So let's just make sure that you understand each of these histograms. So you see this 8 here? What this is saying, the height of the histogram here, which is about, it looks to me to be about maybe 95, says that there were 95 intervals of these 1,000 intervals in which exactly 8 cars arrived. You follow me? And then if we look at, for example, here the number 6, see, 4, 5, 6, that's the tallest one. There were 175 minute intervals in which exactly 6 cars arrived. Now, these distributions are a little bit different from the distributions, the shape of the distributions, for example, of heights of adult men. And it may be a little bit difficult to detect the difference, but these are skewed to the right. There are values that come off to the right here. It's a little hard to tell, but there is an abstract shape that we can figure out by virtue of a mathematical analysis, making assumptions about what's happening with the cars, namely that we're assuming that the arrival of one car doesn't influence how many additional cars come. They're coming more or less independently random times and averaging 6 cars per minute. So there's a mathematical formula here which I will show you. Here is the mathematical formula that you can deduce from abstract terms that predicts how many cars will arrive. That is, how many intervals will have exactly k number of cars arriving during, for how many minutes there will be exactly k cars arriving. So let me give you specific examples so you can see. So 6 is the number of cars per minute, the mean of that. That's the mean number of cars that arrive per minute. And out of 1,000 intervals, we can predict in how many of those intervals we would expect exactly 4 cars to arrive by plugging the number 4, you see the number 4 here and here? 6, the occurrences of the 6 are telling us the mean overall of the number of cars per minute. And then the number 4 is asking the question, how many of these 1,000 intervals will have exactly 4 cars arriving? And the answer is 133.85. And this, if we want to know how many intervals we expect to have exactly 9 cars arriving, you know, a little bit above the average, we would expect 68.84. Now, of course, we're not going to have 68.84 intervals because that's a fraction, and we're talking about whole numbers. So this is giving, once again, an approximation. And here we have the ideal Poisson distribution for this experiment, and you can see how many cars we would expect, how many intervals we would expect 0 cars to arrive, 2.448. How many? 1, you see? So for each one, and how many intervals would we expect exactly 5 cars to arrive? 160.62. So we can now go back to our graphs, our simulations, and superimpose the smooth curve that is the abstract mathematical approximation that we expect to approximate our data. And you see this is the same red curve that's superimposed on each of these 4 data sets, and you can see that they all approximate the data quite well. The value of having a mathematical approximation such as this is that it allows us to analyze such things as the distribution mathematically. We can ask questions such as how many times would we expect more than 9 people to arrive at the toll booth during a minute? And that can affect our decisions, for example, business decisions about how many toll booth places you should have on this highway. So let's, if you change the mean number of cars that arrive per minute, you'll get, of course, a different Poisson distribution. Here you have 10s instead of 6s in these 2 places. And once again, this is going to predict how many intervals you would expect exactly k cars to arrive out of your 1,000 intervals if the average were 10 cars per minute rather than 6 cars per minute. So once again, you see you have a related shape. It's a related shape of what your expected shape of the distribution is. It's related. This one is the shape for an average of 6 cars per minute, and this is the shape for 10 cars per minute. So you can see that the distributions, and oh, by the way, here's the simulation data, simulated data for a mean of 10 cars per minute, and you can see that we've superimposed these graphs, the same graph, the model graph, onto the actual data, and you can see that it fits quite well. And this is the general equation for the Poisson distribution that tells, in this case, the proportion of the intervals in which you would expect exactly k cars if the average number of cars per minute is lambda. The fun thing about looking at families of distributions is that it allows you to take situations in nature and realize that the data that you get from those situations are likely to be modeled by one member of this family of distributions. And let me give you an example. So this is an example that we saw before. This is the number of deaths by mule kicks in the Prussian army over a period of 200 corps years. In 109 of those corps years, no deaths occurred. In 65, 1 death occurred. In 22 corps years, 2 soldiers died from mule kicks, etc. And we can graph this number of deaths by mule kicks in this way because it has the same abstract features that the car arrivals did. Namely, the mule kicks are going to occur randomly. The effect of one person dying from a mule kick doesn't either increase or decrease the chance of another death occurring during the next month, say. It doesn't have an effect. They're independent events. And so when you have that kind of situation where the probability of being killed by a mule kick is basically the same over short periods of time, and that they don't affect each other, they're independent, that's when the graph that you get, the distribution, is going to be approximated by a Poisson distribution. So, and sure enough, we can find the Poisson distribution. This is a curve that comes down here that approximates the distribution. In this case, the mean is 0.61. Remember, the mean is that term that was changed. We looked at Poisson distribution for 6, and we looked at the Poisson distribution for 10, and now this is the Poisson distribution for 0.61. And notice it, by the way, it has a slightly different character, namely, instead of coming down toward 0 at 0, it's higher. It turns out when the mean is 1 is sort of a break point where the character of the curve changes a little bit, but it's in the same family. Another example of where you'd expect a Poisson distribution. A person has done a study of the number of outbreaks of wars in years for 432 years, from 1500 to 1931. For each year, counting how many wars occurred during those periods, and you can make a graph, and you would expect it to be approximated by the Poisson distribution. In how many years was there no war, and how many years one war, and so on. So the point is that when you have a family of distributions, you expect that family of distributions to occur because it's modeling a kind of behavior that the mathematical formula is capturing. So the goal here is not so much to think about the Poisson distribution, especially importantly, but instead to realize the concept of thinking about a family of distributions. A related kind of distribution are the exponential distributions. Once again, this is a family of shapes. The exponential distribution occurs, many of you are familiar with this kind of example. This is an example that occurs if you take a radioactive element like strontium-89, and if you have this strontium, you would expect a certain amount of it to become not radioactive over time, and it has a half-life, meaning that and in a certain period of time, in this case 53 days, you would expect half of the material to have decayed and quit being radioactive. And an individual atom, see, has no memory. Its probability of becoming non-radioactive in the next 53 days is 50%, but if it's made it through 100 days already without turning non-radioactive, it doesn't have any memory about that, its probability is still 50% that in the next 53 days it's going to decay. So that's under those kinds of circumstances, one finds an exponential distribution. And there are, once again, many different situations in which you would expect one member of the family of exponential distributions. It's not just one distribution. There are steeper distributions, namely, instead of the half-life being 53 days, suppose the half-life were 1 day. Then you would have a steeper decay of your material, then you'd expect to have less material quicker. Another family of distributions that is very important are the binomial distributions. And this is another family of distributions, and let's illustrate it by an example. About 2/3 of students who enter high school in the United States actually graduate from high school. That's roughly correct. Now, suppose that we are having a reality TV show. We're constructing a reality TV show, and so we need a lot of participants to start, and we want to get a random group of 50, say, 20-year-olds, and we take this group of 20-year-olds, and we might want to know the sort of education level among those 50, so we might want to ask the question of how many of these groups of 50 are going to have how many graduates. Okay? So in a lot of the groups, about 33 of them will have graduated from high school, because because 2/3 of 50 is 33 1/3, and that's the sort of average number you'd expect. But in some of the groups of 50, there won't be any graduates, right? And in some groups of 50, all of them will have graduated. So what we can do is we can consider all the 20-year-olds in the country, that's one big population, and consider all of the groups of 50, every possible group of 50 that we could select. And for every group of 50, we could ask the question, how many graduates are in that group of 50? And then we can make a histogram that records that information here, which gives us basically, for every number between 0 and 50, it tells us how many groups of 50 have that many graduates in it. So for example, if we looked at 30, we'd ask ourselves, how many of these groups of 50 have exactly 30 graduates? The numbers are absolutely enormous. They're astronomical. The number of groups of 50 from the population of 20-year-olds would be so enormous that it wouldn't be meaningful to us. The numbers would be too big. So instead of that, we measure what proportion of all of these groups of 50 have exactly 30 members in them. So if we take 30 and we go straight up, I think it's this one here, it shows us that about 7% of the groups of 50, of all possible groups of 50, have exactly 30 graduates in them. And if we go up to 31 and go up here and 33 would be one of these top ones, about 12%, 0.12 is about 12% or a little less than that of the groups of 50 would have exactly 33 graduates in them. Well, there are many situations in which we would expect data to have this kind of a distribution. And by the way, this is an example of a binomial distribution. Whenever we look at all possible samples from a given population, we will get a binomial distribution. For example, if we consider all collections of 50 cars in the country, and for each collection of 50, we count how many are blue, we'll get a binomial distribution. If we consider all the collections of 150 people in the United States today and ask how many of them have a cold, we'll get a binomial distribution. Consider all the possible ways that if you flip a coin 15 times, it could land in certain ways. Here's a chart that would show some examples. If you flip a coin 15 times, you could get this outcome: a head, then a tail, then a head, then two, several tails, and then heads, and so on. And for each possible collection of 15 coin flips, for every single possible one, you could count how many heads there were in that collection. And if you did, you would get a binomial distribution that was a histogram that said what proportion of all possible groups of 15 have 0 heads, 1 head, 2 heads, 3 heads, 4 heads, 5 heads, and the middle of the distribution would be centered right about at between 7 and 8, you see, because you'd expect about half of them, most of the collections of 15 would have half of them heads. But there would be some fraction of the distributions that would have 10 heads or 15 heads, like this one has 10. So if we take a collection of a size of 1,600, so this is an example again of a binomial distribution where we have an election coming up, and we ask 1,600 people from a large population how many will vote yes on a particular proposition. If 60% are actually for the proposition, we would expect a distribution that looks like this. It would be peaked at the 60%, which is the correct answer, but there would be some of our collections of 1,600 that have fewer and some have more. And this is just a blow up of that same distribution that shows that most of the high part of the distribution lies between getting 900 and 1,020 of the 1,600 who are actually for proposition B. The binomial distribution has a complicated looking formula here. The point of showing this is just to show that you can actually compute the proportion of the samples that has exactly k elements in each of the samples, and then this is a chart that just shows that if we have a sample size of 10 and 60% of the people are, say, for a proposition, we would expect this kind of a fraction of those samples of 10 to have 6. There'd be about 30% of the, let's see, 10, 20, 25% of the samples of size 10 would have exactly 6, but 7, we'd have about 22% would have exactly 7, and we'd have about 20% that have exactly 5 among samples of size 10. And here we actually have them. So in this lecture, then, we have explored ways of describing the shapes of distributions. And there were generic features that we could describe, namely that a distribution is skewed, or that it's symmetrical, or that it's bimodal, has 2 peaks. And then we talked about specific families of distributions that were modeled by actual mathematical formulas. And these included the uniform distributions, where we could have just flat line distributions, or the Poisson distributions that arose in particular circumstances of random arrivals. And then we had the exponential distributions that arose, for example, in exponential decay of radioactive materials. And then we talked about the binomial distributions that arose from the idea of taking samples from a set. The basic strategy for describing the shape of a set of data, then, is to find some sort of mathematical model that approximates the histogram of the data. In our next lecture, we'll explore the most famous shape of the distributions of them all, namely the bell-shaped curve. See you then.